Hi, my name is Dong J. Lee, and I'd like to talk about Physics Lab 3, Mass of the Black Hole. The objectives of the experiment was first to observe the motion from CSV file to determine the mass of the black hole, and discuss the difference between FNet parallel, FNet perpendicular, and FNet against dPdt perpendicular, dPdt parallel, and dPdt. So the result that I obtained from the experiment by running a Python model here was 3.5218 times 10 to the 31 kilogram, and that turned out to be my black hole's mass, which our kind WebAssign program tells me that I am correct. So let's find out how I figured that out. There are two principles that I've used for this experiment. The first one was the momentum principle, which states that the final momentum equals the initial momentum added to the Fnet times delta t, which we know is impulse, and the change in momentum. And the second line here is the derivative form of the first one, which is divided by the stint of time. So the gravitational force equation here is Fgrav equals to negative g, the gravitational constant, times two masses divided by the r squared times the r hat, which we know is a unit vector. And on Earth, Newton found out that g is equal to 6.67 times 10 to the negative 11 times Newton meter squared divided by kilogram squared. So our given data was star mass equal to 1.989 times 10 to the 30 kilogram, and time was equal to 1 year, which in standard units we're going to put into Python is 86,400 seconds. Black hole's position turned out to be 0, negative 3 times 10 to the 10, and 0. So now let's put these into our code. So we set the origin first by putting in the black hole's location, and we put in star's mass and delta t, and don't forget to pull up this file that WebAssign have given us. And the first while loop, what it does is it sets the both x and component of the velocity of the star that's rotating around the black hole, so that they can actually, when you run this code and see the animation going, and this is what it does. The second while loop determines all the FNet perpendicular and parallel component to us, and this is how I did it. First line, v initial, v final, I set that up by pulling the code from these upper first while loop, and basically I defined the momentum by multiplying mass to these velocities. And delta v and delta p can be figured out by subtracting the initial of them from the final of them. And we know that from the momentum principle that Fnet is equal to dPdt. And after defining p hat, I can obtain dPdt parallel by multiplying this magnitude of dPdt times the p hat. So we know from the first principle of the momentum that Fnet parallel is equal to dPdt parallel. And dPdt perpendicular is going to equal to dPdt minus the dPdt parallel, which we know is again equal to Fnet perpendicular, going back to momentum principle. So after we have defined all these necessary values here, along with the g, which we already knew, we will plug it into this last line of code, which I consider most crucial. And here's the reason why. So the key code is black hole mass is equal to magnitude of Fnet times magnitude of the star position squared all over gravitational constant times star mass. That's because of this equation right here. So we know that one of these mass is equal to black hole's mass. So if I write this in terms of everything else here, then it's going to give me this mass unless I know all these other equations. Since we have defined the net force, gravitational constant, radius, and the mass of the star, and r hat, of course, we can easily find out actual black hole's mass by running the code. So now let's run the code to see if I've actually got it right. And here it tells us that I got 3.521765 times 10 e to the 31, which we know was the answer, and you just witnessed that this animation going around like a star's motion. There were two questions to answer, which first one was to discuss the difference between FNet components and the DPDT components. And according to momentum principle, they are essentially the same value, but the process of finding them is different. And FNet affects the star's motion, whereas DPDT doesn't. And DPDT will only actually tell you about how the star moves. So we only are actually able to know the direction of the star moving, but FNet is actually the reason behind that thing. And what if, question asked, the black hole was replaced into a different, with the black hole of a different mass? And we know that the motion of the observed star remains unchanged. And my answer is that you won't really tell the difference unless you know the definite change in this gravitational constant here. Since we are not given a new constant, we won't really be able to tell the difference. But if the right data of stars' position and velocity were given in that situation, we'll probably be able to come up and assume the difference that's given in the situation. Otherwise, not really. Thank you for listening, and this was Dong Jae Lee's Physics Lab 3 presentation.